Geometry of dynamic tetrahelix and field structures. Part 2. The introduction of the dynamic tetrahelix, which integrates movement into its structure. Part 2. Dynamic tetrahelix. Up until now, the tetrahelix that we have explored have been static and with no overlapping elements. In this section, I'll be using the simulator to introduce some dynamic behavior to the tetrahelix by modifying the twist angle between its elements, which is called twist angle scaling. This will cause the structure of the tetrahelix to expand or contract, and as a result, the elements of the tetrahelix will move along an ever-changing circular path. To examine the inner structure of these dynamic tetrahelix, the tetrahedral elements will be replaced with a simple arc shape. Recursive parenting in the simulator. The Tetrahelic Simulator is based on a physics simulator that uses recursive parenting to define the connection and location of the elements of the tetrahelix. This is an example of a tetrahelix with a length of 3 elements. From a generational perspective, an element can be both a parent and child. In the first generation, element 1 is the parent of element 2, which also makes element 2 the child of element 1. In the second generation, element 2 is the parent of element 3, which also makes element 3 the child of element 2. Relative positioning and tetrahelix motion. The oldest, or first, element of the tetrahelix is fixed in world space and is considered the parent of the next younger element, a child, that is added to the tetrahelix. The child's position is not defined in world space, but in a local space and relative to its parent's output face. A child can only rotate on the axis perpendicular to the output face of its parent. In the next generation, this child is then considered the parent of the next element added, and this process is repeated recursively for each new element added to the tetrahelix. Accumulated tetrahelix motion. When a child moves, it has no effect on the position of its parent or ancestors. However, when a parent moves in space, its child and all its descendants move along with it, because their local space reference has changed as the parent moves. Every child will inherit the accumulated motion from all its ancestors. As a result, the youngest element moves the fastest, since it has the most ancestors to accumulate motion from. Twist angle scaling description. The default twist angle step of the classical tetrahelix is 120 degrees, but the simulator allows this step to be dynamically modified. For example, if the twist angle step is changed to 150 degrees, then the simulator will do the following, based on the current subsequence definition for the tetrahelix. Digit 1 would change the twist angle for this connection from 120 degrees to 150 degrees. Digit 2 would change the twist angle for this connection from -120 degrees to -150 degrees. Digit 0 in the sequence is unaffected and remains at a 0 degrees rotation. The oldest element is fixed in space, and twist angle scaling will cause the younger elements of the tetrahelix to extend or contract, which creates motion. The simulator treats the elements of the tetrahelix as massless objects. Twist angle scaling. These two diagrams illustrate what happens when the twist angle is scaled to a different angle. If the twist angle is scaled to 150 degrees, the absolute value of the element rotation is increased by 30 degrees. If the twist angle is scaled to 90 degrees, the absolute value of the element rotation is decreased by 30 degrees. For any element rotation that uses 0 degrees, they do not change. Twist angle scaling example. The oldest, or first, element of the tetrahelix is fixed in space. Starting with older elements first, the simulator makes incremental changes to the twist angle. As the older elements rotate, all the younger elements connected to it have their frame of reference change and as a result, experience the accumulated motion from the older elements. The simulator repeats this process and the tetrahelix starts to move, with younger elements moving faster than older elements. Closing the gap on loop tetrahelix. Twist angle scaling will now be demonstrated on a loop tetrahelix with a sequence of 1 1 1 2 2 2. A small increase to the twist angle, from 120 degrees to 120.43 degrees across all the elements, will cause the tetrahelix to extend until the gap in the loop is closed. Now, the output face of the youngest element aligns with the input face of the oldest element. A closed loop circuit can now be created by making a connection between the youngest and oldest element of the tetrahelix. Overlap and element collisions. In this example, if the elements of the tetrahelix overlap, a collision is detected, and its elements will get displaced. In the next section, the collision detection will be turned off, which will allow us to explore the behavior of tetrahelix when overlaps are allowed. Wave propagation in loop tetrahelix. In this example, the gap of a loop tetrahelix is forced closed without doing twist angle scaling. The forced connection between the oldest and youngest element of the tetrahelix create a torque force on all the connections of the tetrahelix as the gap is forced closed. This causes the tetrahelix to buckle and produces a snake-like movement that ripples along the path of the loop. This demonstrates how the loop tetrahelix can efficiently propagate wave motion. The shape of the elements doesn't get distorted by the simulator, but the connections between elements have some springiness, which allows for a little bit of twisting in the connections. Also notice the standing wave patterns that are created as the elements move along the path of the loop. Reassembly of loop tetrahelix. This video illustrates the versatility of the dynamic structure of the loop tetrahelix. Making a sudden, large change to the twist angle will cause the loop tetrahelix to break apart. However, the parent-child relationship remains intact, and these connections will allow the tetrahelix to reassemble itself in its original order. Part 2 wrap up. This concludes Part 2 of the presentation on dynamic tetrahelix. In Part 3, the harmonic behavior of the dynamic tetrahelix will be explored.